Hello everyone, I'm Eric and today we'll be learning Pythagorean triples. So Pythagorean triples, you probably all heard of it. A squared plus b squared equals c squared, and then we're just gonna draw a good old right triangle. Not very right, who cares? 3, 4, 5. Yes, 3 squared plus 4 squared equals 5 squared. It's the most beloved of teachers. And there's actually a fun fact about how Egyptians used to make pyramids. So they tied 12 knots into a string to give them 12 equivalent line segments and tied them into a circle. And then using the 3, 4, 5 theorem, they got a right triangle, just like that. And I'm gonna mark it right here, 3, 4, 5. That's the right triangle they've got. So that is how ancient people used to make right triangles. Of course, now we can just go into Keynote and get a right triangle out by ourselves. So you guys probably know what we are gonna do next. Are there infinitely many Pythagorean triples? Okay, let's think about it. Pythagorean triples, A, B, C. Let's say we randomly choose a positive integer d. It could be any integer d, except negative and zero integers d. And then we'll multiply d into the equation. So it's dA squared plus dB squared plus dC squared. And you guys probably know why this equation is basically the exact same as this equation, because if we open up the parenthesis, and I'm gonna write it over here, d squared a squared plus d squared b squared plus equals d squared c squared, and this should actually be equal. So, and we can see that we can basically cancel out those d squared, bye, and it's basically the same. So there are infinitely many Pythagorean triples since there are infinitely many positive integers. But we don't want these kinds of Pythagorean triples. They're too boring. We can just get infinitely many at a wave of the hand. So what we're gonna do is we're gonna define something called the primitive Pythagorean triples, and we're gonna call it PPT, and not PowerPoint. So AB3, they have no common factor, and they satisfy a squared plus b squared equals c squared. Then ABC is a PPT. So let's see, 3, 4, 5. They have no common factor, and they also satisfy this equation, so it is a PPT. But 6, 8, and 10, while it does satisfy this equation, it is not a PPT because they have a common factor of 2, since they are all even numbers. So let's get out some examples real quick. Let's say 3, 4, 5, the most familiar, and the second most familiar, 5, 12, 13. We'll need a much longer list to actually see the pattern by ourselves, but I'll only write 2. So look, 3, 4, 1 odd, 1 even. 5, 12, 1 odd, 1 even. So A, B have different oddities, which means they're 1 odd, 1 even. And also 5, 13, C is always an odd number, and we're gonna write it like this. ABC looks like one of A and B is odd and the other even. And C is always odd, but is this true? We'll have to prove it. So in order to prove that A, B have different oddities, we'll say that since there are only 2 numbers, A, B, they can either be both odd, both even, or 1 odd, 1 even. So let's say A, B are both even. Actually, I'll give it a different color. So if they're both even, then C is even as well. And if they're all even, as I had said before, it is not a PPT because they have a common factor of at least 2. So bye-bye. No, both odds. Both evens. Now let's say both odds. A and B are both odds. Then C is also even. 2 odd numbers have a sum of an even number. So there must be 3 integers, x, y, z, that satisfies A equals 2x plus 1, B equals 2y plus 1, and C just equals 2z. Now, since we wrote these 3 equations, we can substitute it into the a squared plus b squared equals c squared. And we get 2x plus 1 squared plus 2y plus 1 squared equals 2z squared. And we open up the parentheses as always, and we get 4x squared plus 4x, and we're gonna leave the plus 1 and we're gonna write it later. You'll see where it goes. And then plus 4y squared plus 4y, and the plus 1 coincides with this other plus 1, and we have a plus 2, and it equals 4z squared. Now you probably already noticed 4, 4, 4, 4, 2, 4. They have a common factor of 2, and they do. So we'll divide both sides by 2, and unfortunately I'll have to do a clear all. So it's 2x squared plus 2x plus 2y squared plus 2y plus 1 equals 2z squared. Now we see 2x squared, 2x, 2y squared, 2y, they're all even, and 1 is odd, and an even number plus 1 is always an odd number. And 2z squared, the d squared can be either an odd or an even number, but since there is a times 2, then it must be an even number. So right now you're telling me that an odd number equals an even number, and that is absurd. So A and B cannot be both even. It will not be a PPT, cannot be both odd, or else we'll get odd equals even. So it can only be 1 even and 1 odd. After we prove this, it is increasingly easy to prove that C is always odd, because let's say A is the odd number, B is the even number, and we'll see that A squared is odd, B squared is even. An odd number plus an even number is odd, so C is always odd. After we prove this, we're going to do some magic, and A squared plus B squared equals C squared. Now you're probably wondering what I am going to do. I'm going to subtract both sides by B squared, so that we get A squared equals C squared minus B squared. And for those who don't know, A squared plus B squared, A squared minus B squared can always simplify to A plus B and A minus B. So C squared, so C squared minus B squared can always simplify to C plus B times C minus B, and we will collect some examples to see if we are right. let's say 3, 4, 5. Then a is 3. 3 squared equals what? 5 plus 4 times 5 minus 4, which is 9 times 1, which is undoubtedly correct. Now we'll see 5 squared, the 5, 12, 13 example. It equals 13 plus 12 times 13 minus 12. And we get 25 times 1. Now we'll as I've said, we'll need a grander list to actually tell the pattern by ourselves. But we see that 9, 1 and 25, 1, they do not have a common factor, and we are going to prove it. So in order to prove it, we'll say set D, and D is D is a factor of D is a factor of C plus B and C minus B. And if D is a factor of both, then D is a factor of these numbers added together, and also a factor of these numbers subtracted. C plus B minus 3 C minus B. And if we add them together, we get 2C. If we subtract them, we get 2B. So 2C and 2B are both even numbers. So D must be a factor of even numbers. And then we see that if we multiply these two together, these two terms together, we get a squared, and a is odd. So a squared is also odd. So right now D must divide an odd number and an even number. And the only choice for D, therefore, is 1. In other words, they do not have a common factor except 1. So also, we notice that 9, 1 and 25, 1, they're both squares, 3 squared, and this is 5 squared. Now, later, we will prove that if A times B equals x squared, then A and B must also be square numbers in order for this to actually happen. We will prove it later on. And so I'm just gonna put this theorem right here. And we see that C plus B, C minus B, both square numbers without a common factor. So let's say C plus B equals S, and C minus B equals T. And also, you guys probably know S is greater than T, and they're both greater or equal to 1. And S and T do not have a common factor, or in other words, they are relatively prime. So now we'll find C and B, and we'll just get them independently out. So let's plus these two equations together. We'll get 2C equals, this is actually S squared, T squared. We'll get S squared plus T squared. Then C is S squared plus T squared over 2. Now if we subtract these two equations, we get 2B equals S squared minus T squared. And divide both sides by 2, we get B squared equals S squared minus T squared over 2. And we found B and C for themselves. Now let's find A. And we do know that C plus B times C minus B is A. So it's a squared. So a squared equals s squared t squared. And if we take the square root of each side, we get a equals st. So now we have the theory. A equals st, b and c equals these two fractions. And also s is greater than t, which is greater or equal to 1. And they're chosen to be any odd integers with no common factors. Now we'll have to check if this is correct. And the best way to do it is to substitute it into the original equation and take out the parentheses. So let's do that. St squared plus 2, s squared minus 2t squared over 2 squared equals, well, we open up the parentheses as always. We get s squared t squared plus 2 over, this is going to be a long fraction, s to the 4th power minus 2 times s squared times t squared plus t to the 4th power. And for those who do not know, a minus b squared equals a squared minus 2ab plus b squared. And we see that s squared t squared equals 4s squared t squared over 4. Oh, and I also forgot to make this a 4. And now we see 4s squared t squared negative 2s squared t squared. Then we have a positive 2s squared t squared left. So let's combine those, and we get 4. It's s to the 4th power plus 2 squared t squared plus t to the 4th power over 4. And we see that the only change of this between this fraction and this fraction is the change of this negative and positive, and it actually makes a big difference. So before, we can only write it as s squared minus t squared to the squared. Now we can write it as, well, before it's t squared. Now we can write it as s squared plus t squared squared. So this is basically c squared, and right now we're going to take the square root. So we get, we're actually gonna write it again. C squared equals 2 squared over s squared plus t squared squared. And if we take the square root of each side, we get c equals, well, s squared plus t squared over 2. And this is the same as this. So it is proven to be correct. And today we'll only talk this much. Tomorrow we'll get out our unit circles. So goodbye and see you next time.